Okay, as we finish this problem, we're going to have a directional derivative at a particular point. They're always going to have to specify a point, but they did give us the direction that we wanted, and that vector v was not the right length. It had a length of radical 29. If you divide its components by radical 29, then you've got a unit vector. Well, look up here, up in blue. You technically don't have to rewrite this as a dot product, my word. I mean, you certainly can, but we could say f sub x. Well, that f sub x times a, and then we'll say f sub y times b. Well, that f sub x is a 2xy cubed. Then we'll have this 2 radical 29 plus, and then we'll have 3x squared y squared minus 4 times a 5 all over radical 29. But guess what? We're really going to say I have a specific point that we need to look at. You can see that vertical bar. We're really saying from this point on, let's let x equal 2. Let's let y be -1. And then clean it up. So the calculus is done. Right now it becomes number crunching, and you just gotta get things cleaned up a little bit. So, and it might get ugly. Let's be honest there. -1 cubed is -1. 2 times 2 times 2 is an 8. So we've got -8 over radical 29. Over here, 2 squared is a 4. 4 times 3 is 12. -1 squared is a 1, so I've got 12 minus 4. This whole thing's an 8. 8 times 5 is 40. And from here, you just combine your like terms. You don't have to rationalize. But that value is the rate of change of your function f as you're moving in that particular direction. Okay, we doing okay? Let's go to the very bottom here. You could say, what if you move to 3 variables? What if all of a sudden you had a function of x, y, and z? Well, the gradient would be the partial derivative of f with respect to x as the x component, partial derivative of f with respect to y for the y component, partial derivative of z for that function for the z component. You could also write that in IJK notation. Very similarly, as we just saw up above a little while back, the directional derivative could also be thought of as the gradient of f dot producted to the unit vector. So tell you what, let's take a look at another problem here. And we're asked to find a gradient for part A for a function. And then we're supposed to find a directional derivative at a particular point, 1, 3, 0, but also in a very particular direction. So, keeping in style with what we've been doing, let's take a derivative with respect to x. What do we get? This should just be sine of yz. Let's take a derivative of f with respect to y. What do we get? xz cosine of yz. Remember, y is our variable that is changing. Z would be thought to be a constant, right? We need the chain rule there. And then finally, f sub z would be, help me there, what do we get? xy, yep, cosine of yz. Very good, very good. So, for part A, they could say, well, find the gradient of f. The gradient of f is simply f sub x, comma, f sub y, comma, f sub z. And, it doesn't take you too long to work that thing out. You get sine of yz, comma, xz cosine of yz, comma, xy cosine of yz. And you're done with part A. As we venture to part B, one thing that we're going to have to be extremely cautious about, guys, is whether the vector in question is in fact a unit vector. I have to be honest with you, most of these problems, what do you think? Do you think it will be? No, you're all shaking your heads. You know the author. You know, it's not just Professor Stewart. It's everybody, right? I mean, so you'd look at the length of V, and you'd say, well, what is that length? Oh, Pythagorean theorem in 3D, right? You know, you take all these components. So it's 1 plus 4, which is 5, plus another one. So if I haven't made a silly mistake, I guess that's radical 6, right? Right. So it's got a length of radical 6. Well, as we're venturing off for our unit vector, you could say, well, you know, and V, by the way, here I go. I really kind of prefer the bracket notation. You know, you get the 1, comma 2, comma negative 1. Well, would we all agree readily that if we divide original vector V by its length, that its new form, its new vector is going to now have to have a length of 1, right? So that's your real unit vector, right? So for part B, what they're really saying is, hey, you want to find your directional derivative, you know, for f of x comma y, it's going to be your gradient dot producted to u. And, you know, I want to show you that you can actually write out a dot product. I mean, it's fine. You can do that. You should see it written that way too. So we're going to say dot that with this ugly thing right here. We get 1 over root 6, 2 over root 6, negative 1 over root 6. And if I just wanted to find a general directional derivative for that unit vector, you know, we'd get the sine of yz times 1 over root 6 plus, well, we'd get xz cosine of yz, multiply that times 2 over root 6. And then we'll say plus, well, then we'd have xy cosine of yz times a negative 1 over root 6. However, we're going to be plugging in the point. Now, if memory serves, I think it was 130. Was that right? 130. Okay, so, you know, as you do that, let's just take a look at what's going to happen. You look right here. Z is 0. And in fact, if you look at all of these trig functions, guys, when you plug in a 0, would you agree the trig arguments, what is inside all 3 of those trig expressions, that's going to have to go to 0? Right? I mean, that's just a simple observation right there. We know that the sine of 0 is 0. The cosine of 0 is 1. So that gets cleaned up pretty quickly. That first expression is completely out of the way. You know that if z is 0 right here, well, my goodness, now that middle expression is going to completely get wiped out also, right? But x is equal to 1, y is equal to 3. So you'd get 1 times 3 is 3. Don't forget, you also have this negative 1 over root 6 to multiply out there. So despite having a frightening length for that whole directional derivative in general, once you substitute that point in, the first expression and the second expression, you know, they're going to cancel out with zeros multiplied out. It really works out pretty quickly. Okay? We doing all right? All right, we're getting near the end. Look, let's just take a look at this theorem right here. Suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative, you could say, what's the biggest a directional derivative can ever get to? Answer, surprising maybe at first, it's the length of the gradient vector. The length of the gradient vector. And it occurs when u is the same direction as the gradient vector. That can sound so funny to kids, and you might be thinking, is that right? Is that really true? first of all, review. Let's just do a little bit of review. Going back to chapter 12, you've got two vectors that got dot producted together. Do you remember that it was really the length of A times the length of B, vector B, times the cosine of the angle between them? So here was vector A, here was vector B, and this was the angle between them, right? You can say, well, that's your dot product. You could work it out term by term, x component times x component plus y component times y component. Or if you want a real quick way to work it out, length of vector A times length of vector B times the cosine of theta. What am I getting at? Let's look. See, here's something so cool, guys. You could say, hey, this thing right here, the directional derivative, is a dot product. Sometimes we wonder, why did we complicate things? Why did we turn something into a dot product? I didn't need it. Well, maybe it gives us a new way of looking at it. You could say, according to what we just saw in our review, this is going to be the length of the gradient vector, the length of the unit vector, times the cosine of the angle between them. Wait, what's the length of a unit vector? The length of a unit vector is 1. Wait a minute, that means the directional derivative is the length of the gradient vector times the cosine of the angle between them. So you ask yourself, what would make this gradient vector magnitude times cosine as large as possible? When would cosine become as big as possible? When theta equals 0. When theta equals 0, you're going in the same direction, aren't you? Right? Think about it. Two vectors have 0 degrees between them. You'd say, oh, that means that, they're literally on top of each other. If you put them tail to tail, they'd be going in the same direction. So this theorem, it's pretty cool. You can say, hey, I know what the biggest directional derivative could ever possibly be. The largest it could ever be is the length of the gradient function vector right there. So let's do our last problem right here. And it says, find the rate of change of f at a point 2, 0, and it's going from point P to point Q. And then for part B, we'd like to know in what direction does f have the maximum rate of change, and what is this maximum rate of change? And so in other words, what's the biggest rate of change we can ever see? Guys, I don't think I even need to tell you at this point. Look how we can get started. Partial derivatives. F sub x of this thing, what is it? E to the y, and let's take a derivative with respect to y. Don't we get that? Right? And then you could say, no, wait a minute. As we're looking at a point here, we're going from point P to point Q. So visually it would kind of look like that. How did we get vectors in the past when I said start at one point, end at another? Let's subtract head minus tail, right? End minus beginning. So we could say PQ is going to be end minus beginning, right? Here's your ending x value minus your beginning x value. And by the way, we want to write that as a vector, pardon me. And then we'll say a 2 minus 0. And you can say, well, my goodness, I guess that's really negative 3 over 2, negative 1.5, comma 2. Do you think this vector has a length of 1? No. Good night. We knew that all along, didn't we? My gosh, all of a sudden kids, though, can get a little bit intimidated. They'll say, whoa, look how ugly this thing is. This is 9/4 plus 4. Yeah, 4, though, as a common denominator would be 16/4. Wouldn't you agree with that? What's 9/4 plus 16/4? Well, they actually gave us something nice to take a square root of. Square root of 25 over 4 is 5 over 2. And forgive me, I forgot to put absolute value around there. That's really the length of vector.